So let's start. So today I'm going to present one of the latest projects that we have done here in Intelligent Machine Lab at Carleton University in Ottawa, so Canada, which is the Grounded Multi-modal Conversation for zero-shot visual question answering. We've done these projects with our colleagues here, as I said, in IML. So let's start. So first of all, regarding the visual question answering, so as we all know that, but by emergence of the VLM, visual language models, the highly interest absorbed by the visual question answering tasks from the researchers in the domain. So what we know about the VQA or visual question answering is just given an image. We are trying to ask questions, the textual questions on a given image. So, but using the only VLMs, so visual language models for this task is not that good because we are facing some challenges with the VLMs in the context of the zero shot learning. So what are those challenges? The first of all is the limited factual knowledge. So for example, the most of the VLMs, they lack of the factual knowledge. In fact, so more specifically for the complex questions. So for example, if you ask some questions regarding, let's say in this way, if you have a glass upside down on a table, besides that, if you have a bottle of water on the table, and if you ask question, if we pour the water onto the glass, if it flow into it or not, most probably most of the times the VLMs will answer yes. Okay, and which is wrong. So the other problem or the other challenge that we are facing is the common sense reasoning. So since the VLMs are pre-trained with the limited amount of the the data, so they lack of this common sense knowledge. So another problem that we are facing with the VLMs are the over reliance on visuals. So and most of the time the VLMs ignores the textual signs. For example, if we if you have an image of image of a shop, which with the with the turned on the lights and some people's inside the shop, and but with the textual sign of the closed behind the door, if you ask the if you ask the VLMs if the shop is open or not, so it will ignore the closed sign, closed textual signs, and it will say, yes, it's open. Just, by relying on the visual signs, the people inside and the turned on the light. So another problem with the VLMs for the VQA is the ambiguity. They are weak when we have very ambiguous questions or very complicated images. What I mean by the complicated images is the images with lots of objects at the same time. Okay. So for example, just as a small example here. So if we have this image, the image of sandwich here, and if we ask the VLM, where can this red vegetable be found? So most of the times, most of the VLMs will answer inside the sandwich. Okay, so which is wrong. So now what's the solution for, to overcome these limitations? The solution for, these problems are combining the capabilities of the LLMs with the strengths of the VLMs. Okay, so to have kind of VLM LLM conversation. Okay, so why we try to combine the LLMs with the VLMs? Because of the strength points of the LLMs, which are, as we all know, the LLMs by themselves, they are very strong in reasoning and language understanding and textual text understanding. And also, they are good in knowledge integration. So in terms of, so if we give the LLMs lots of, facts, so they are good in inducing the, the in concluding the right answers. And also the other strength points of the LLMs is that they can interpret the nuanced questions, and they are good in building the reasoning chain. So, I mean, so we can use this point for, the to handle the diversity of the complex questions. So, for example, just as an example, for the same problem that we saw before, so if we ask the where can this red vegetable be found? So, if we force the LLM to ask another question from the VLM, what type of vegetable is present in the image? Okay, so the VLM will answer the tomato and lettuce. So then the LLMs can reason that since tomato is red, so we can say it can be found in a garden. Okay, so this is the idea of the combining the LLMs with the VLMs for the VQA problem. But then we have also some limitations in the existing VLM-LLM framework. So, by the way, so this combination of the VLMs and the LLMs is not a new topic. So previously, several works have been done on, this domain, but they have some limitations. All of them have some limitation. The first of all, it's that the all those systems are rely on entire images. So, for example, when the LLMs ask the VLMs and VLMs try to answer the questions, all the VLMs, all the methods before, so they try to focus on whole image instead of, fine grained patches. So because of that, they mostly miss the key regions of the image that are relevant to the question. The other problems that we found is that holistic focus. So they are most of the previously presented methods are struggling with the fine-grained question. Okay, if the question is relevant to the specific part of the image, so most of the time, those combined the previously the presented combined frameworks are not able to answer them. And then, so the last one is the limited visual grounding. Okay. So, and here, the problem here that we see most of the time, so sometimes the LLMs may misinterpret the VLMs, the answers, so since the LLMs are going to, create the conversation or ask the question based on the VLM's answers. Sometimes the LLMs misinterpret the answers of the VLMs, and based on that, they are asking the wrong question. So, for example, here in this example, in this image, when we ask the how many children are in the street, so the VLM by itself, it says the image based on the captions. So they say the image features a young girl playing with water hose in the middle of a street. So, but if you look at here, there is another young boy behind this little girl. So, but the VLM by itself, it neglected it, it ignored this young boy. Okay, but then since the LLM asked the other question based on this caption, so Then it asks the what other children, if any, are present in the image. Okay, so then VLM tried to answer this question again, since it only look at this younger from the previous step. Okay, so they said there are no other children present in the image. So these are the problems with the previously presented VLM-LLM framework to tackle the VQA problem. So, but what we have presented, considering the problems that I discussed, so we presented the grounded multi-modal conversation for zero-shot VQA. So here, instead of focusing, just considering the entire image at the same time, okay, we try to focus on different parts of the image. Okay, so the key idea here is, first, the region grounding. We focus on question relevant regions instead of the entire image, as I mentioned, and also imitating the how human being tries to improve the understanding, their understanding. We try to establish a kind of iterative conversation between the LLMs and VLMs. So the model we propose composed of 5 components: the locator, captioner, question generator, and question responder, and finally the inferencer. So usually in the VLMs, so not usually, always, just if you want to use the VLMs to answer the question, so the answer to the question, the VLMs by themselves are responsible to make the answers to the questions. But here instead of VLM, the responsibility of the generating the final answer is with the LLMs, not with the VLMs. Okay, so this is just it's a kind of example here. So if we have this image here, what's the person doing on their PC? So we have locator. So first we will find the different paths relevant to the questions. Okay, by the locator. Then for each found patch, we ask the VLMs to caption it, to describe it. So then for each patch, we ask the LLMs as a question generator to create several questions that answering those questions may help to answer our first question. Okay, then the question responder will respond, all those questions, and at the end we will give all the textual information that we gathered during the previous steps to the inferencer, which is the LLM here again, to asking to generate the final answer. So if the LLM or inferencer here is confident by the generated answer, so it will generate the answer. But if it's not confident, so it will iterate over the the previous steps to create more questions to answer the new questions, and then combine them, integrate them, and again try to find the answer with more confidence. Okay, so now let's look at the framework step by step. So as I mentioned, the first step here, or the first module that we have in our model, is the locator, which is a pre-trained open set visual grounding model. Okay, so this grounding model works by the textual prompt. So, and the responsibility is just to extract question relevant patch. For this part, we tried different, types of prompting, and we came up with, just giving the question to the model and simply asking it to just find the objects or the patches relevant to the question. So then, for example, here, as you see, the locator finds, two patches here. So this one and this one. In the second step, our second module, which is a captioner, so it's a pre-trained VLM. We ask the captioner to describe each patch, okay, as much as it can. So, for example, the captioner will generate these captions for two previously found patches: a computer monitor sitting on a desk with a monitor, a keyboard, and a cup of coffee. So then for the step 3, the LLM will we ask the LLMs to, to generate the auxiliary question about each patch relevant to the first question, the main questions that we ask. And that we think that the LLM thinks that answering to those questions can help the LLMs to find the answer to the main question. Then in the step 4, the VLM will answer those auxiliary questions. Okay. So for example, here the question generator, this is our main question. What's the person doing on their PC? So also we create the caption for that. Then the question generator will generate, the several questions, and then the question responder will tries to answer those questions. Sorry. So, and question responder here is another VLM. Okay. So then at the end we have the inferencer, which is a LLM, pre-trained LLM. So it attempts to answer the question considering all the previously generated questions and answers, plus, the main question. Okay. Then if confidence is low, so if the confidence for the found answer was low, so it will repeat over the previous steps 3 to 5. Otherwise, it will generate the answer. The capability of this model is about the explanation of the decision. Since, the LLMs are good in explaining the reasoning process. So when the LLMs generate the answers, okay, so we ask the LLMs to explain why he decided to go with that answer. Okay, so now let's move into the implementation details. So for the modules and the models, for the locator, we use the grounding dyno, which is an open set model with 172 million parameters. For the question responder and captioner, we use the same VLMs. We try several, different VLMs with different architecture, more specifically Blip2 and Instruct Blip and Lava. And for the question generator and inferencer, we use the LLM, the same LLM. The primary LLMs that we used was GPT-4o mini, but we also tested different models like the GPT 3.5 Turbo and Llama models, also Mistral, and we also tried the mixture of experts model like the Mistral 8x7 billion Instruct model. So, and about the data sets, so we did our experiments on 3 different data sets. The first one was VQA V2 data sets, which is based on the COCO images. It's the kind of standard data sets for the general VQA problems, and the focus on focus of these data sets is on vision, language, and common sense reasoning. Also, we tried the out of knowledge VQA dataset or OK VQA dataset, so which is the extended version of the VQA V2 datasets, but requiring the external knowledge. So the answers often go beyond the visual content. So, I mean, to answer the question, usually the VLMs or the models need the external knowledge as well. And finally, the last dataset that we tried was the syntax VQA, which is a data set focusing on the syntax understanding. So on the image, the main focus on understanding the textual clues in a given image. And regarding the performance, so first of all, we evaluated our model, the performance of our models based on the accuracy, and we did the comparison between the results of our model, and we compared it with the individual end-to-end VLM models, the Lava model, Blip2, and Instruct Blip as well. In addition to those models, the end-to-end VLMs, we compared our model, the performance of our model, with the state-of-the-art the VLM-LLM based model for the VQA task, which was the ideal GPT. The difference between our model and the ideal GPT was, the ideal GPT was focusing on it focused on the whole entire image instead of the patches of the images. So, and as we can see here, so in general, I would say the results of our model in average is almost 10% better than the end-to-end VLM. And it also outperforms almost 22.5%, in average, the ideal GPT model. So also another things that I would like to mention here is about how we evaluated the generated answers. So since the LLM is responsible to generate the answers, and the answers in a form of the free text, so they are not the concrete, the words. So sometimes, in each run, the LLMs, produces, the answers with different wording. So to resolve these problems, we use the LLM as judge technique, and we ask again, GPT for Omni to evaluate the generated answers by the inferencer by comparing it to our gold standard. So, and that's it. And also, we did some experiments on a number of the iterations that our models take into account to generate to repeat the conversation between the LLMs and the VLMs. So the average number of iterations per questions with 95% confidence intervals. So we saw that in average, the maximum number of the iterations that our models need to answer each question is less than 2. Okay, so at most 2 iterations would be enough. So, but we define the maximum number of iterations as 4, which always, the real number of iteration was below this predefined threshold.
Abbas, can I ask a quick question?
Yes.
What's special about 4?
Yeah, actually, so we decided to go with 4 because, we wanted to compare the results of our model with the ideal GPT. Okay, so and in ideal GPT, it was taken as 4. So the iteration number was taken as 4. And in most of all other, the LLM, VLM combined model, okay, so the threshold was set to the 4.
So it's kind of accepted standard, I guess.
Yeah, actually, yeah, I would say kind of, but there are some problems. If we go with the higher number of the iterations, so it will increase the cost, right? So we wanted to
So kind of balance.
stick to the commonly used threshold values for this threshold, and avoiding the increasing the cost.
Okay,
Okay,
thanks.
yeah, no problem. So then this indicates the most questions are resolved efficiently without needing the full iteration budget. Also, so the results confirm that our model is both effective and computationally efficient in zero-shot VQA tasks. So just as a qualitative analysis, so you can look at here 2 examples here. So for example, for the previously seen problem, where can this red vegetable be found? So for this question, the original answer is garden, but the predicted answers but different VLMs. For example, the Believe 2 said in sandwiches, Lava said in sandwich, Instruct we've said tomato, Ideal GPT said restaurant. But our model, just taking the iterative conversational model and conversational steps that I explained previously, it generated this answer in a garden, and also it explained why it came up with this answer in garden. Or for the another example from the, let's say, the scene text VQA or ST VQA dataset. So here we have this image, 2 baseball players, and the question is what number is written on the black shirt. Okay, so which is 28. So just again looking at the results from different models. So we see the Believe 2 said 2, Instruct Believe said 25, Lava said 20, and Ideal GPT said 25. But our model, again, by just grounding the image into different patch relevant to the question, and asking the generating the question and asking the VLM to answer the question, and then inferencing all the information is gathered from the VLMs and the LLMs. So it says it generated 28 by this explanation. One of the provided caption indicates that there is a player wearing black shirt. So, and one of the captions specifically mentions that the black jersey has the number 28 on it. Okay, so and based on this explanation, so based on this reasoning, it says the answer is 28. And finally, just let's conclude the presentation. So our model GMC VQA, we introduced the grounded multimodal conversation for zero shot VQA problem, and we combine the capabilities of the VLMs being good in vision tasks and the LLM, strengths of the LLMs in reasoning through the region-based conversations instead of, holistic view on the image. And then it enables selective focus on question-relevant regions, enhancing the accuracy. And as we saw previously, our model outperforms the traditional end-to-end VLMs and prior VLM LLM framework across, VQA, V2, OK VQA, and syntax VQA datasets. And thank you.